Hi everyone, my name is Victor Engelmann and it's been a while, huh? So some of you may have already seen on my Facebook page that I have ordered two books on Amazon, this one here and this one. And you might have already guessed what I'm going to do now. I want to make a video series, or actually multiple video series, about Linux and the Linux kernel. So this here is going to be the first of these video series, and this one is going to be about Linux from scratch. And what's Linux from scratch? Well, if I completely oversimplify it, I would say that Linux from scratch is a Linux distribution. But if you go to LinuxFromScratch.org, to the download section, you will immediately see that I just completely oversimplified things, because if Linux from scratch was just a normal Linux distribution, you would get an ISO file there, you would download it, put it on a USB stick or on a CD or a DVD, and then you would be able to boot from it and have a running Linux system. But on LinuxFromScratch.org, you will get a PDF file instead. So here I've printed that PDF file out. This is actually only half of it. Why am I telling you that a PDF file is a Linux distribution? Well, Linux from scratch is actually a collection of instructions, so to say. If you follow these instructions, you know, it's like download this tarball, extract it, compile it, and if you follow all these instructions, you will get all the components of a Linux system, and then it tells you how to put them together so that you can boot from that system in whatever way you want. But why would you want to do that? I mean, there are easier ways to get a running Linux system, right? Well, for me, it's learning. I know Linux systems pretty well. I've been using Linux for 16 years now, and I've used a lot of different distributions. I just want to make another step down, and I think Linux from scratch really dissects Linux so that you really get to know each and every program that it contains, and each and every directory, each configuration file, each option in each configuration file. So that's a real dissection of a Linux system, and I think this will give you and me real great knowledge about Linux systems, the anatomy of them, and another thing that you might want to do is maybe you want to build an IoT device. So this here is a Raspberry Pi with a screen attached. Raspberry Pis can run Linux systems. Maybe you want to build an IoT device based on Raspberry Pis. Or maybe you want to build your own IoT device and try to get Linux running on that so that you can communicate with it over the network or something. Or another idea that I'm thinking of is stripping the Linux kernel down to a minimum that is required to run it on a KVM virtual machine, so that you would be able to bundle such a system with any program, and then any program, like whatever, a DHCP server, a DNS server, whatever, could be bundled with such a system and then distributed as a virtual machine, and then running a program would just be much easier, because you wouldn't have to fiddle with configuration settings or whatever. You'd just download a virtual machine, stick it in your KVM and run it, and you're good to go, right? That would make it much easier to move from one hardware to another. You could just take all your virtual machines, move them to a different hardware, so you wouldn't have to reinstall and reconfigure everything when you change your hardware. Or maybe you want to start your own Linux distribution and not have it based on Ubuntu or Debian or Arch or whatever. So that would be another idea that you could have. Let's start talking about how you can actually do that, how you can make such a Linux from scratch system. So I think a good starting point, even if I'm repeating myself now, is looking at the boot process of a computer, because in the end we are talking about being independent from any provider of anything, whether it's Microsoft or some distribution, whatever. So I think it's a good idea to know the hardware that you're running on, at least to some degree. And those who have seen my other video series will already know this, but I don't want to go into details as much as I did there. So just bear with me, and if you've seen my other video series, you can just skip ahead. So your computer has a main board, okay? And on that main board, you will have a CPU, a hard disk, or some other form. I mean, we don't use disks anymore, but I still say hard disk. And you have some random access memory, RAM, and a BIOS, which is just a ROM chip or an EEPROM, to be more precise. And if you want to know more about these topics, shout out to Ben Eater. He has some very good video series about hardware design, and two of his video series are absolutely great. One about building a computer on breadboards. So he basically builds a main board and uses an MOS 6502 processor as a CPU. And the other video series is about creating a CPU on breadboards. Great video series, absolutely loved them. I will put links in the description. But let's continue. So when you start your computer, the first thing that will happen is that your mainboard is going to run the firmware that is stored in your BIOS. An EEPROM is like a storage device. Okay, so this is where your firmware sits. And maybe that's transferred to the RAM. It could run from the BIOS actually, but so let's say this is your RAM. The RAM is basically just a huge array of bytes. And so let's say first thing that we do is we copy the firmware to the RAM, and then we tell the CPU to run the code from there by setting its instruction pointer to maybe the first byte of the firmware. Not necessarily, but let's say, for simplicity, let's say it does it like that. Now the firmware of the mainboard that came from the BIOS will then basically just tell the whole computer to talk to the hard drive. Okay. So for simplicity, I will pretend like it was still disk-based. I mean, the communication with hard drives is still really pretending like it was disk-based. So we discussed that in my other video series. Even if you have an SSD or an M2 hard drive, they will pretend that they would have a disk. Okay, so if this is your disk, then the first sector of that disk is the master boot record, MBR, and the firmware of the mainboard will tell the CPU to talk to the hard drive and copy the master boot record into the RAM also. Okay. And then the firmware will tell the CPU to start running that code from the master boot record by setting the instruction pointer in there. What you have on that master boot record is called a bootloader, and that bootloader knows just some things about partition tables and file systems. So the bootloader will then be able to look at something like /boot, you know, the Unix directories start with /. It's like C: in Windows. So to look at /boot/ whatever comes from its configuration file, I'll just call it kernel. You know, it might be called VM Linux, whatever magic, but yeah, so the bootloader will then copy that into the RAM and will then tell the CPU by setting the instruction pointer to start running the kernel. Okay. So this is as far as we've got in my first video series, because at this point we started writing this kernel, and everything that came after that was really hard-coded in the kernel. But that's actually not a good idea in reality, because stuff shouldn't run inside the kernel, because running in the kernel means it has very high access rights, and that's a security problem, for example. But of course, things should not do more than what they are there for. So a kernel is really just there for communication between different processes, including driver processes or system service processes, or daemons as they are called in the Unix world. And so the kernel shouldn't, for example, know about network protocols, or it might not have to know about hard drives, although that's debatable. I mean, Linus Torvalds says that they tried to move all the file system stuff out of the kernel into kernel modules, and they were able to do that. It's not like they had failed at it. It's just that things were more complicated and slower. So you had no benefit. So why would you want to do that in the end, right? So yeah, what happens in reality is stuff doesn't run inside the kernel. The kernel is really just there for communication between things. So instead of doing stuff itself, the kernel will then just start some initialization program. Like in the old days, you would have a program named init. That would be the system v init. These days, it's more common to have a systemd initialization, and so most of what happens in the boot process is actually done by the initialization systems. So they would look at their configurations, and then their configuration might say, hey, bring up this service and that driver, like your network driver and some DHCP client service, for example. So to bring up your network, to mount some hard drives and stuff like that. Of course, this would normally be the boot partition. And then you would have a separate root partition. So part of the initialization process would actually be to mount this partition depending on the file /fs tab. So /fs tab will have an entry, for example, to mount this partition as / or root. And then for convenience, you would also mount your boot partition on a subdirectory boot. Okay, and this needs to be done pretty early in the process because, I mean, when your initialization system then wants to start some programs, start some daemons, load some drivers, they are loaded usually from the root partition, and well, it needs to be mounted to do that. Okay, so I think that's enough about the boot process of computers in general and Linux systems in particular. So let's talk about how we are gonna set up our Linux system such that it can be booted on our machine. So the BIOS is just there. It just has its firmware, and I'm not going to touch the firmware because it's too risky for me. I don't want to brick my machine. And this whole communication with the RAM and the CPU is all hardwired in the mainboard. What we need to do is, at this point, we can hook into it by providing it with a hard drive that has a partition table, a master boot record, then a partition with a kernel, a boot partition, and then a root partition with all the programs and daemons and drivers and stuff, and also the configuration files. So that's going to be the point where we start. We will create this whole hard drive. My hard drive is actually rather full, so I'm not going to do this in a virtual machine, but I will put this on this little USB key. This is 30 gigabytes. LinuxFromScratch actually advises you to take something of 30 gigabyte size. They say 10 gigabytes is the least you should have, just for all the files and compilation stuff and in between. So 10 gigabytes is what you really need to build your system, and then you should have something like 30 gigabytes if you really want to do stuff with your system afterwards. So yeah. This is going to be our hard drive. I'm going to use fdisk to put a partition table on it, put ext2 file systems on the partitions, and then we will fill these partitions with programs and drivers and daemons. And in the end, we will then need to run some grub programs to really put the bootloader in the master boot record, and then we will be able to boot from it. Okay, so how are we going to do all that? So as I said, I will use this USB key or USB stick. And the USB stick is, again, just like a big array of bytes. The first thing we'll need the master boot record, and then we will have a boot and then we have a boot partition with about 100 megabytes, and the rest is going to be the root partition. So how do we do all that? The LinuxFromScratch book subdivides the whole process into 3 stages. In the first stage, they would call the build machine. In the second stage, the host machine. and the third stage is the target machine. So in the first stage, you would just run on your regular PC with with the operating system that you have installed there, and you would just use the package management from your operating system to create some things, to install some packages like GCC, make, whatever, autoconf, autotools, just a tool chain, okay? And this tool chain, they don't really use that much, because in the next step, they tell you to download a lot of files, like the Linux source code, grub, core utils, also GCC, make, Bison, all that stuff. Now the reason why you need all that is the first stage is relatively short. You know, you just installed these things, downloaded these things, and now you will just use this tool chain to create a new tool chain, and that new tool chain is going to be the one that we will be using more than this one. So one of the first things that you will do is let's give these things names like A, B, and C. So remember, this GCC from your distribution is going to be a GCC that will run on A and produce binaries for A. But your machine B might be already a different machine with a different processor, so you might already not be able to use this GCC to run on B. So what you would do now is create a tool chain that can run still on A. That's important. We put on B a tool chain that can run on A, because at first we will still run on A, but when that runs on A and produces binaries for B. So this is one of the first things you will do. You make a new tool chain using this GCC and this source code to build a so-called cross-compiler to create this GCC. And then you will use this cross-compiler to compile a lot of the other stuff, not everything, but a lot of the other stuff, like I think Bison is in there, Flex, autoconf, automake, M4, you know, another tool chain, right? So, and since we are using this GCC here that produces binaries for B, all this is going to be able to run on B. And then we will also use this compiler and the GCC source code to produce another GCC which can run on B. You know, because when we've built it with this GCC, then it runs on B. But this is going to be another cross-compiler that will then produce binaries for C. Okay? And once we have compiled a lot of these things, including core utils, you know, core utils is an important package here. Core utils contains really basic stuff like mkdir and cd and mv and rm. You know, just the lowest level stuff of managing directories and creating them, removing them, deleting them, moving them. Why do we need all that? Because once we have compiled all this, there comes a really interesting stage. Because at this point, we will go into a change root environment, ch root. And we will have this mounted under /mnt/lfs, for Linux from scratch, mount Linux from scratch. By the way, we will store that mount point in an environment variable. Okay, so we've mounted it there, put everything in there, and then we will change root into there. And after we've done that, this is a really interesting point. After we've done this change root, it's gonna be as if we had booted from this machine or this system. So this is an issue of isolation. We will still actually be running on the kernel from machine A and have booted from the grub on machine A, but everything outside of mnt/lfs is going to be invisible, and everything below mnt/lfs is going to be going to look to the system as if mnt/lfs was our root partition. Okay, so that's really an interesting point, because at that point we are so isolated here from our original system. It's going to be as if we had booted from this system, and that's really an important thing, because you have really a good isolation then. If you are using this GCC, you are absolutely not able to accidentally link against some libraries from here, because these libraries are just going to be like not existent at this point. Okay. And once we have achieved that, then we can start using this GCC, because now we are running on B. I mean, you can take the USB key at this point, go to a different machine. If your B is a different machine, this is a point where you can take your USB key, put it in a different machine. That different machine still needs to have its own operating system. And then you would need to do all this mounting stuff, setting the variable on that machine, but we are going to do this on one machine anyway. So at this point, again, we will start using this GCC to compile all these source codes again. To create the things in /bin/lib/ whatever sbin/lib64 and so on. And then we will really compile everything, all the packages here. And since this is a compiler for C that produces binaries for C, this is going to be able to run on C then. And interestingly enough, we will also build another GCC here. But I mean, all the GCCs we've had so far will not help us when we are on C. So we will need to create another GCC that runs on C and produces binaries for C. Okay, and once we have done all that, then our root partition is filled. We need to compile Linux and grub to put on the boot partition, and then use grub to create the master boot record. And at this point, we would be able to boot from our USB stick. except that, well, just because we have a kernel, we haven't told it to do anything. You know, it needs to start the init system, and the init system needs to be configured so that we need to tell it which services to run, which drivers to load, and so on. So in the end, we also need to write all the configuration files. Because, yeah, in the end, I know most of these programs already, and just compiling them isn't that interesting, to be honest. I mean, I think all of them, or almost all of them, just use the auto tools, automake, autoconf. So you will usually just have this classic triplet of configure, make, install. And then a lot of text is going to be running from the bottom to the top of the screen very fast. And also you will usually have some parameters to configure that will tell it to put the resulting files onto your root partition, so somewhere relative to the mount point of the root partition. So it's going to be some form of $LFS in here or down here. And that's really not so interesting, but and it's going to take quite some time. I think they said it would take about 5 hours. Maybe we can speed it up with parallel compilation, but yeah, as I said, this is, I don't think it's such an interesting part. I think the configuration is more interesting, but then I will use this time for all the compilation to talk about the directory structure. You know, which directories are there, why are they there, what would you put there normally, and also the selection of these packages. You know, why are these packages in there, what do they provide, which programs are in there, why would you want to have these programs. So I hope this is not going to be all too boring in the end, and I hope this was not too boring for you. Yeah, if you liked this video, like it, share it, subscribe, and maybe turn your ad blocker off while you're watching these videos. That would help me a lot. And yeah, see you next time. Bye.